Hello and welcome to my presentation with the topic of filtration simulation with GeoDict 2022, the latest and greatest features. My name is Mehdi Azimian and I'm responsible for the filtration business unit of Math2Market. Well, I start my talk with a short introduction regarding modeling and simulation of filtration at different scales with the GeoDict software. For today's presentation, I have chosen three highlighted topics. These are among the latest and greatest features we developed and improved in GeoDict software in order to better study and investigate the filtration through filter media and filter elements. These topics are simulation and optimization of filter media. Here, for example, for face masks, simulation of droplet coalescence through filter media, and last but not least, the simulation of air filtration at rooms with air purifier. Well, through the COVID-19 pandemic, Math2Market developed further features in GeoDict software to design, model, simulate, and optimize filter media and filter elements at different scales, as you can see in this slide. And of course, many GeoDict users worldwide expanded their activities towards digital design of modern and optimized filters. And nowadays, besides modeling and simulation, and of course optimization of filter media, as you can see here at the left side, and then also single pleats and filter element, we're now able to precisely simulate the flow through nanofibrous media considering slip lengths. And in the macro scale, we have more capabilities, especially when simulating the flow through any complicated geometry of filter with housing, and also cross-flow filtration simulations, for example, for simulation of membranes. And last but not least, as we can see here at the bottom, we have recently expanded our solutions for air simulations at room scale, considering air purifiers. So now I start with the topic of simulation and optimization of filter media, for example, for face masks in this presentation. So it's known that the filtration characteristics of a filter depends mainly on its filter media, and by understanding and then optimizing the nano and or microstructure of a media, the macro properties can be modified and optimized. Here in this slide, you can see on the right side the microstructure of a two-layer filter media of a well-known face mask, which is imported and segmented in GeoDict from micro CT scan of the media with a scanning resolution of 0.4 micrometer. We can see here at the bottom the fine layer, and on the top the pre-filter or support layer of this filter media. In this case, the main filtration task, and of course the main part of the pressure loss, is due to the fine layer at the bottom. And of course, the optimization of this layer can mainly affect the filtration behavior of the whole mask. So on the filter media of the face mask shown in the previous slide, the simulation of the filtration with GeoDict and experiments were done. Here we can observe the results done by Berger et al. From Heilbronn University of Applied Sciences. The simulation with GeoDict, shown here with red color, was conducted considering no electrical charge. And when we considered experiments with the filter media, discharging the media 24 hours with isopropanol, we can observe a very good agreement between the simulation and experimental results. And here on the very top, we can see here the purple points showing the experimental data of the new media with electrostatic charge. And we can also, let's say, simulate the case considering electrostatic charge with GeoDict. However, the goal here was to initially run flow and filtration simulations through the original media and validate the simulation results for further optimization studies. So for the optimization of the filter media, if we consider here the fine layer of the filter media, which has the major role in filtration and pressure drop, we need to define, let's say, some lists of desired variables. In this optimization example, we have selected solid volume fraction, mean fiber diameter, and media thickness of the media as variables. And when we define list of variables, if you consider, let's say, 5 different solid volume fractions, 6 different mean fiber diameter sizes, and also 6 different media thickness variations, we come, let's say, to a total number of sample variations of 180. And considering the stochasticity, having 3 multiple samples per design, we come to a huge number of total samples as 540 samples. Of course, this high number of samples can be modeled and afterwards to be simulated with GeoDict using automation capabilities of the GeoDict software with Python scripts. And this saves, of course, a lot in physical tests, in material consumption, and also saves a lot in time and personnel costs. So we can observe and analyze the simulation results of such optimization studies in GeoDict using 3D plots. In this slide, we can see the results, for example, for constant media thickness of 128 micrometer. In the upper plot, we can observe the pressure drop as a function of solid volume fraction and also the mean fiber diameter. And in the plot below, we can see the filtration efficiency by weight is demonstrated again as a function of solid volume fraction and mean fiber diameter. And we can find out the best designs out of these huge samples where we have the highest filtration efficiency and at the same time the lowest pressure drop. And let's say the best 3 or best 5 designs out of 500 designs can at the end be proposed for, let's say, further testings and prototypings. So the next topic is the simulation of droplets coalescence through filter media. So this work was done under BIGOFIL cooperation project, which is a publicly funded project. The word BIGOFIL stands for bicomponent fibers for gas oil filtration. The aim of the project is to increase the efficiency of droplet separating filters, or let's say COALESCER filters, through the experimental and simulative development of novel filter medium made of bicomponent fibers. Here's the list of the academic and industrial partners working and collaborating on this project, each having a task to accomplish the final goal. And the Math2Market task was to create and implement a model to describe and simulate the coalescence in the GeoDict software, which is successfully done and it's under final improvements. So the coalescing filtration is the separation of 2 phases. For example, the removal of water or oil aerosols and droplets from a gas. And here, the designing and optimizing new innovative cross-section shapes for fibers as bicomponent fibers, as shown at the left side, in order to manufacture optimized fibrous COALESCER media, as shown in the middle, and then for the end use as a coalescing filter media, a filter element, as shown at the right side, are the steps which were carried out or which still have to be carried out for this project. As you can schematically observe in the middle image, when, let's say, aerosols are injected into the media here from the left side, and more aerosols are filtered, the coalescence will occur among the aerosols contacting each other. And when the size and the corresponding mass of a Coalesced droplet increases, then this droplet may be detached and discharged from the media as soon as the gravitation force becomes larger than the adhesive forces between droplet and fiber. So what has been done in GeoDict to simulate the droplets coalescence of two droplets is mainly based on the combination of distance functions of the centers of gravity and those of the solid surfaces weighted according with the contact angles. The droplet shape of the new generated droplet can be approximated depending on the contact angles, and this method is of course much faster than a complete two-phase flow simulation. Comparison was done between the simulation results from GeoDict and Star CCM, showing a very good agreement of more than 80% of the voxels when, let's say, observing the new droplet shapes and forms. And a model, of course, for the detachment or removal of the coalesced droplets from the filter medium is also developed and is under final modifications. So in this slide, we can take a look at a video. You can see the simulation of droplet coalescence on a single fiber as more and more smaller droplets coalesce and generate a larger droplet as a very simple example to show how this works in the GeoDict. In this slide, we can observe a realistic case. So we modeled a fibrous media, which is a COALESCER filter media from Alstom München, with application for oil removal from compressed air. The media is made of fibers with 3 different diameter size distributions, having quite fine fibers, with the finest fibers in the range of sub-micrometer as diameter size. And first of all, what we did is we generated this model with FiberGeo, and we run flow and filtration simulations to compare and validate the simulation results with the experimental data of Alstom München. So here you can see the filtration efficiency, which was measured for aerosols with a mean aerosol diameter size of 0.3 micrometer at a mean flow velocity of 5.32 centimeter per second, and also the initial pressure drops from experimental data and also the simulations. A bit deviation may exist, and this is mainly due to the fact that the mean aerosol size is reported here as 0.3, but in the reality we have, let's say, a distribution of aerosols which is probably in the range of 0.2 to up to 0.5 micrometer, and depending on how we exactly define this aerosol size distribution also for the simulation based on the experiment, we may have this a very slight deviation. So in this slide, we show a video which shows the coalescence of the oil aerosols through the filter media, and we can see the oil aerosols which are in the airflow are tracked through the media, and the filtration of aerosols, the coalescence and detachment of aerosols are simulated here. And we can see when new aerosols are injected into the domain from the top, and when more and more aerosols are filtered, the coalescence will occur. And when the size and shape of new generated aerosols, let's say, exceeds from a threshold value, then this droplet can be detached and discharged from the outlet. More technical details about this topic will be presented by Dennis Hoch and Andreas Weber in their presentation afterwards. And here, the last topic of my presentation, which is the simulation of air filtration at rooms with air purifier. So the goal here is the correct selection of an appropriate air purifier and also the selection of its optimum location in a room. For such simulations, the input data that we need, as shown here on the top, is the geometry of an air purifier and rooms as STL or OBJ formats. And besides that, of course, we need also the fluid, which is, of course, air, and the particle or aerosol parameters. And the output results or output data is mainly the aerosol concentration or the variation of aerosol concentration as a function of the filtration time. So for this kind of simulations, first of all, the room CAD geometry, including the walls, the desks, chairs, even the persons, are imported into GeoDict and voxelized. Moreover, the CAD geometry of an air purifier is imported. And what we did here, we let's say we can position the air purifier at different locations here, shown with P1 in the front, P2 at the back, and P3 on the sides. And with such simulations, we can investigate the effects of air purifiers with different flow rates, and also the effects of their positioning in room can be analyzed by running filtration simulations with GeoDict. This is an example that we did for this study. After importing the geometry of the room, we have a computational domain size with approximately 245 millions. And in the next slides, we are showing the next steps. So the detailed steps to follow are the following. First of all, as mentioned, we need to import the room and air purifier geometries as STL or OBJ files. Then we position the air purifier at a desired location. We simulate the airflow with FlowDict module, and then we track the particles or aerosols using the computed flow field. This is done currently with ADDIDICT module, and at the end we visualize and analyze the results. So here we can see the initial airflow simulations without considering the aerosols or particles in the meeting room that we simulated using an air purifier, here shown with the red color in the front. For flow simulations, we use the Lear solver, which is based on adaptive grids, and we solved Navier-Stokes equations. Here we can see the flow streamlines caused by the air intake of the air purifier in front of the room, and the result legend here on the right side shows the velocity distribution, showing quite high velocities in the vicinity of the air purifier. The runtime of this flow simulation was approximately 6 hours using 16 parallel processes. So after computing the flow streamlines, what we have to do is to define an initial concentration for aerosols, or let's say a total number of aerosols in the room. We have to define the properties of these aerosols, for example, their size and density. And if I start this video, we can see this initial concentration or this initial numbers of aerosols in the room. And here we do the tracking of aerosols with ADDIDICT module of GeoDict. We can observe here, let's say when we start the simulation or when the air purifier starts to intake the air, of course we see the streamlines, how the flow will be, let's say, intake into the air purifier. So the suction side is here at the bottom of the air purifier, and the outlet is here on the top. And of course, the time required for minimizing the aerosol concentration in the room is the key factor for choosing the appropriate air purifier and also its best location in the room. All right, in this slide, we can see the influence of air purifier different locations or different positions. As mentioned, we can test different locations for the air purifier and rerun the simulations. With this, we can investigate the effective air purifier location on aerosol concentrations in the room. So these 3 simulations were done with the constant volumetric flow rate of 1,440 meter cubic per hour. And we can see that the front and side positions have a better or faster effect in reduction of aerosol concentration. If we take a close look, for example, at position 3 or the side configuration, at a volumetric flow rate of 1,440 meter cubic per hour, we can extract more detailed information. For example, we can see that we achieve a 50% reduction in concentration of the aerosols happening after almost 4 minutes. And we can also see that we achieve a 90% reduction in concentration happening after almost 13 minutes. Furthermore, the influence of air purifier operating speeds or volumetric flow rates can be investigated in details. Here we tested 3 various flow rates of 1080, 1260 and 1440 meter cubic per hour at position P1, which was the case that the air purifier was in the front of the room. When we take a look at the aerosol reduction as a function of time, we can observe that the higher flow rate cleans the room faster. But here the second highest flow rate is also the same, almost the same fast, but can save in energy consumption and reduce the operating noise. And therefore, as a short conclusion of these investigations, we can find out that the operating speeds or volumetric flow rates and also the location or position of the air purifier are 2 important factors for their optimal functionality in a room. All right, this is the end of my presentation. Thank you very much for your attention and looking forward to your questions and comments.